So the general equation for alternating EMF is E naught sine omega t plus some constant. Okay. So when you square this, it becomes E naught square. This part is a constant. Okay. E naught is the peak EMF. That's a constant value. Sine square omega t plus constant. And as time varies, this part of the equation will be variable. Okay, the sine function keeps on changing. So the square of the EMF keeps on changing. So we'll be interested in the average value of the square. Okay, we should write it like this: E square averaged. There's a difference between E average squared and E square averaged. Okay, in fact, E average in one complete cycle is 0. When you square it also, it will be 0 only. But when you first square it and then average it, the average won't be 0. Okay, because the negative terms won't be there if you first square it. So there's a difference between averaging and then squaring, and first squaring and then averaging. Okay, now we want the average of the square. So we should do the square first, which we have done. And now we have to take its average. Okay, the average of this function will be E naught square is a constant, and this variable part is the sine square function. Sine square function's average is half. So the square of the average of E square will be E naught square by 2. Okay, just remember the average of the sine square function is half. Okay, based on that, you will be able to solve problems. Next, quite often in problems, we'll be required to calculate the root mean square value of the function. Okay, RMS literally means root of mean. Mean means average of square. Okay, let's consider the sine square function itself. Let y is equal to sine x. Sine function, not sine square function. Let y is equal to sine x. If you first square it, it becomes sine square x. The function itself becomes sine square x. Next, you take mean of the square. Mean of the square means average of sine square x function. I told you in the last class, angular brackets indicate average values. Okay, average of sine square function is half. Now you take root of mean of square. That becomes root of half. That is 1 by root 2. So what does this tell us? It tells us that the root mean square value, RMS value of the sine function is 1 by root 2. Okay, if RMS value of the sine function is 1 by root 2, the EMF equation you have is this: E is equal to E naught sine omega t plus some constant. This thing's RMS value is 1 by root 2. Then what will this thing's RMS value be? Can one of you tell me quickly? The sine part's root mean square value we got. And the sine part is multiplied with a constant E naught. So what will the overall root mean square value be?
E naught by root 2.
That's all. E naught by root 2. Okay. So for this function, the RMS value is this, just the peak value divided by root 2. Fine. So answer this question, all of you. An alternating EMF is given by this equation. E is equal to, let's say 10 sine 100 pi t plus some constant angle pi by 2, phase angle pi by 2. So it's of the standard form only, E naught sine omega t plus phi. You can write that standard form also here. You can compare them. Okay. So based on this alternating EMF equation, tell me all these values. What is the time period? Time period I'm indicating by T naught. What is the time period of variation of this EMF? What is the frequency of variation of this EMF? What is the average EMF in the positive half cycle? What is the RMS value of this EMF? Solve quickly, I'll give you 2 minutes. Okay. See, generally this function E naught sine omega t plus constant. Can you tell the formula for time period of this function?
2 pi by omega, sir.
Yeah, generally for sine omega t function, the time period is 2 pi by omega. And frequency, as always, is the inverse of time period, omega by 2 pi. Okay, so time period here becomes 2 pi by, in place of omega, we have 100 pi. 2 pi by 100 pi is 1 by 50 seconds. That will be 0.02 seconds. Frequency is inverse of time period. It will be 50 per second, 50 cycles per second. You call it as 50 hertz. See, I was telling you in the last class and the class before that also, the current that we get or the voltage that we get in the household power socket is an alternating voltage. Fine. And the usual power that we get in India has this frequency of 50 hertz. Okay. You can even see electronic appliances, their specification, there will be a label or a metal sheet behind the device having specifications at what voltage it operates, at what frequency of voltage it operates. Mostly you will find 50 hertz only. Okay, they'll write something like 220 volt, 50 hertz AC. Okay, because that's the frequency at which they are designed to work. That's the frequency at which we get power from the household power circuit also. Okay, next, average EMF in the positive half cycle. Isha, can you answer? Pradyun, can you answer? Simple. See, positive half cycle. The average of the sine function in the positive half cycle is 2 by pi. When the sine function is multiplied with E naught, then the average becomes 2 E naught by pi. And E naught is the peak EMF, which in this problem is 10. So 2 into 10, 20 by pi. Whatever is the unit for E, same unit you'll use here. I'll just write units. Next, RMS value. RMS of the sine function is 1 by root 2. Okay. And if the sine function is multiplied with E naught, then the RMS value becomes E naught by root 2. E naught is the peak EMF 10. Divide by root 2. The answer is 5 root 2 units. Pradyun, did you understand? Okay. Rishi, your answers are correct only. Okay.
Sir, 1 second. I have a doubt.
Hmm.
So the first answer I gave it as what? Oh, 1 by 50 pi.
No,
How is it
pi
0?
gets cancelled. Pi gets cancelled. 2 pi by omega, no? 2 pi by
Oh,
100
yeah.
pi. Pi gets
Yeah,
cancelled.
sir. Yeah. Okay, sir.
Okay. So if you are given an equation of alternating EMF, you can tell these things from that equation. Average value, RMS value, time period, frequency. And what is the name given to omega? What is it called? Omega is called angular frequency of the function. And see, these are quite common. I think you would have first come across omega angular frequency in the chapter oscillations, 11th class. In oscillations, you have the general oscillation equation, x is equal to a sine omega t plus phi. Okay. Then the chapter after that, waves, general wave equation also, you have y equal to a sine kx plus or minus omega t. There also you have that omega. Omega is called angular frequency of oscillation. Okay. And in 12th class, I think this is the first case where you come across this. And next you will have electromagnetic wave equation. In that also omega will be there. And after that, that's all. I think after that you won't use omega anymore. Huh. Okay. So basically in oscillating functions, that omega value is called angular frequency. And angular frequency is different from frequency, just frequency. Okay. Just frequency is inverse of time period. That is omega divided by 2 pi. It's not directly equal to omega. Okay. It's omega divided by 2 pi. We have written here also. Fine. So we know how to deal with the alternating EMF equation. Like we know how to find average RMS and all. So generally any equation of this form, you can follow the same steps to get the average value and RMS value and time period and so on. Now we'll enter into this chapter, we'll enter into the physics of this chapter. What you essentially learn in this chapter is when an alternating voltage like this, okay, like what? Let's take a simple equation to start with. When an alternating voltage like E naught sine omega t, okay, I'm not writing the constant inside the bracket. We'll deal with it later. When an alternating voltage like this is applied to different circuit elements, when it is applied to a resistor, how to find out current, how much power will be dissipated, all those things. When it is applied to a capacitor, how much charge will get developed on the capacitor, how much energy will the capacitor store in it. All those things you should be able to find out. When it is applied to an inductor, how much current will flow through the inductor? What will be the EMF induced across the inductor? What will be the energy stored in the inductor? All those things you should be able to find. And finally, we will learn how to deal when an alternating voltage like this is applied to circuits consisting multiple elements, like resistor, capacitor, inductor, all three of them, or maybe only two of them, all those things. So what we learn in this chapter is how to find out or how to deal with circuits which have alternating EMFs in them. Okay. And the circuit symbol for alternating EMF is this, just a wave symbol inside a circle. Okay. This indicates alternating voltage. This indicates direct voltage, means constant voltage. Okay. Till now, for batteries, we used to use this because battery maintains a constant EMF. Okay. So for alternating voltage, we'll be using this. So the first thing we'll learn is how to deal if this alternating voltage is applied across a resistor. Only a resistor, nothing else. Okay. Assume the resistance is R and it is connected to a source of alternating EMF. And the equation for the alternating EMF is this simple equation, E naught sine omega t. Okay. Generally, what happens when you apply potential difference across a resistor? Anyone? If you apply potential difference across a resistor, what happens? Or if you apply voltage to a resistor, what will happen? Or connect resistor to the terminals of a battery, what will happen? Current will flow. What will happen if you apply potential difference between 2 points? Current flows from high potential to low potential. Now see, this is an alternating EMF. So what happens is, for some time, the left terminal, for some time means for half cycle, okay, let's say the positive half cycle, the left terminal will be at positive or high potential, the right terminal will be at low potential. Okay. The same applies to the resistor. Left end will be at high potential, right end will be at low potential. In that case, current will flow in the rightward direction. That means in that case, current will be flowing this way. But when the negative half cycle is going on, okay, for the other half time period, the EMF will change its polarity. That side will be high potential, this side will be low potential. Now current will flow in the reverse direction. Okay, makes sense. Now through a resistor, current always flows from high potential to low potential. If left end is at high and right end is at low, it flows to the right. If right end is at high and left end is at low, it flows to the left. Okay. So when you connect an alternating EMF to a resistor, you get an alternating current in the resistor. For some time, current will be flowing this way, and for some time, it will be flowing the other way. So it keeps changing direction. That's what we call as alternating current. Current which keeps reversing its direction frequently. Okay. Is this clear? Is the idea clear?
Yes, sir.
Equations we still have to discuss. Okay. Tell me generally, how are voltage, current and resistance related?
Ohm's law.
Ohm's law, tell the equation.
V is equal to IR, sir.
V is equal to IR. So I is equal to V divided by R, where V is the potential difference across the resistance R, not somewhere else or not between some other 2 points. Whatever is the potential difference across that particular resistance is what you need to consider. Now look at this circuit that we have taken. Okay, this alternating EMF circuit. We are applying an alternating voltage across that resistance. Okay, but whatever is the potential difference developed by the source, that itself will be the potential difference across this resistor. Therefore, the current in this loop can be expressed like this. It is the applied EMF divided by the resistance. And the applied EMF is an alternating EMF. The resistance can't do anything about it. So it becomes E naught sine omega t divided by R. Is this step clear to all of you? We are just writing Ohm's law, I is equal to V by R. The voltage we applied is the alternating voltage, that's all. So nothing special in this, nothing confusing in this. So when an alternating voltage is applied across a resistor, you get an alternating current like this. And how do we say this current is alternating? As time passes, for some time, like for half cycle, the sine function will be positive, and the other half cycle, the sine function will be negative. So current keeps becoming positive and keeps changing from positive to negative. So for some time it will flow clockwise, sometime it will flow anti-clockwise. That's what is alternating current. Okay. So we got the current equation as I is equal to E naught is a constant, R is a constant. Put them aside. Sine omega t. Okay. One of you tell me, as time varies, you know the sine part will vary. This is the variable term. What is the maximum value of the sine function as time keeps on varying?
1, sir.
Plus 1. Minimum value?
-1.
-1. So it varies from -1 to +1. If the sine function varies from -1 to +1, then what can you say the current varies from and to? When the sine function is -1, current will be minus E naught by R. And when the sine function is +1, it will be plus E naught by R. Okay. So from 0, it can rise to plus E naught by R, or it can fall to minus E naught by R. Maximum current is E naught by R. So we call this term as the peak current, I naught. So if you write E naught by R as I naught, then the current can be expressed as I naught sine omega t, where I naught is E naught by R. Any doubt in this? We got the equation for current through the resistor. Any doubt in this? Pradyun, Isha, is this clear?
Yes, sir.
Okay. Now let us discuss further about this. The EMF function we used is E is equal to E naught sine omega t. The current function we got is I is equal to I naught sine omega t. Since both are positive sine functions, whenever this becomes +1, means whenever the EMF reaches its peak value, positive peak value, at the same time, the current will also reach its positive peak value. Okay, obviously, whenever the sine omega t becomes +1, it has to become +1 in both functions. Okay. Whenever this becomes -1, at the same time, this will also become -1, means both will go to their negative peak at the same time. So these two functions vary in the same manner. What do you call such functions? Or what are such functions said to be in? Okay. When two oscillating functions oscillate together, yeah, Pradyun, what you said is correct. They are said to be in phase with each other. Okay. So the current, the alternating current passing through a resistor and the alternating voltage applied across it will always be in phase with each other. That is one observation we can make. Next, you have the EMF equation, you have the current equation also. Use the EMF equation. E is equal to E naught sine omega t. This is the voltage we are applying. And we know the resistance is R. Can one of you tell me the formula for power dissipated by a resistor? Power dissipated by a resistor.
Sir, I square R.
That's in terms of current, correct only. In terms of voltage, I got one answer as V by R. V by R is not correct. V by R is the current. V is equal to IR, I is equal to V by R. What is the power dissipated by a resistor in terms of voltage?
V square by R.
V square by R. Okay, where V is the voltage across that resistance. Fine. Now here, the voltage is a variable voltage. If the voltage is variable, the power will also be variable. That's all. So you can say that power dissipated by the resistor is E square by R now. And in place of E, you put this function. Okay. It becomes E naught square sine square omega t divided by R. That's the power dissipated by the resistor as a function of time in terms of EMF. You can write the same function in terms of current also. P is equal to I square R. Substitute this I function in that. You will get nothing wrong, nothing like special in that. But look at this power equation. E naught square is constant, R is constant, put it aside. The variable term is the sine square omega t term. As time varies, this keeps varying. That means the power dissipated by the resistor also keeps varying. And can the sine square function ever be negative? Anyone? Can the sine square function ever become negative?
No, sir.
Obviously not. It's a square. Okay, it can be 0 or positive only. Okay, any value of time you substitute, it will either be 0 or positive. That means the power dissipated will either be 0 or positive. And that makes sense. See, we discussed this in the chapter current electricity. How does a conductor or a resistor dissipate power? When electrons move through the conductor, they undergo collisions. That is what is resistance. Okay. And whenever an electron undergoes a collision, it loses all its drift velocity. Means it loses kinetic energy. Where does that go? It is released as heat. Right? Now, whether the electron is moving to the right or to the left, it will undergo collisions. So whether positive current flows or negative current flows, power like heat will keep on getting dissipated. Doesn't matter which way the current is flowing. Okay. That is why power dissipated is never negative. Okay. For whether the positive half cycle is going on, current is flowing clockwise, or the negative half cycle is going on, current is flowing anti-clockwise, energy will keep getting dissipated. Okay, and the equation is also telling us the same thing. Okay, so there's a variable part here, that's fine. Can one of you tell me what are the extreme values of the sine square function? What is its minimum and what is its maximum?
0 and 1.
0 to 1, correct. When this is 0, the power is 0. When it is 1, power is E naught square by R. Therefore, peak or maximum power dissipated is P naught, that is E naught square divided by R. Had you used current equation and written power as I square R, this would have become I naught square into R. Okay, that I think you can derive on your own also, not a big deal. Okay, that's the peak power, maximum power, but that will happen at very few instants because sine square will be 1 only when the angle is pi by 2, 3 pi by 2, 5 pi by 2 and so on. Other times it will be less than 1. So at other times the power will be less than E naught square by R. Sometimes it will become 0 also. So we'll be interested in knowing what is the average power dissipated by the resistor. Can one of you tell me the average value of this function? There's a constant term and a variable term. Think carefully and tell me what is the average of that function. What is the average value of the sine square function?
One by 2.
Half. And the sine square function is multiplied with E naught square by R, which is a constant. Then what will be the average of this entire equation? I don't understand. Like, what is so difficult in this? The average of the variable part is half, and it's multiplied with a constant E naught square by R. Then the average also will get multiplied with that constant. Then dissipated power, average power dissipated will be E naught square by 2R. Okay, let's take an example just to clear this. Suppose there is a distribution of numbers. Say 1, 4, 5, 20, 15. What is their average value?
9.
10, 10, 20 is 30, 45, 45 divided by 5 entries. The average value is 9. Okay. Now let us multiply every entry with the constant value. Let's multiply all of them with 3. Then what will the entries now become? 3, 4 3s is 12, 5 3s is 15, 20 3s is 60, 15 3s is 45. These are the values now. When every term is multiplied with the same constant, 3, these are the values we got. Now tell me the average. 3 plus 12 is 15, 15, 15 is 30, 30, 60 is 90, 90 plus 45 is 135. 135 divided by 5 entries now becomes 2, 7, 27. Okay. For the original number, the average value was 9. When all the original numbers are multiplied with the same constant, then the average is also getting multiplied by the same constant. No, 3 into 9. Fine. So same logic we are using here. The variable part is sine square. We know its average is half. Now at all times, the sine square function was being multiplied with E naught square by R. Then finally the average also will get multiplied with E naught square by R, and the power will become E naught square by 2R, average power. Okay. All three of you, is this clear?
Yes, sir.
Isha, did you understand?
Yes, sir.
Okay. Now we got expression for average power dissipated. You can write this in terms of current also. In terms of current, if you write, it will be I naught square into R divided by 2. In terms of voltage, it is E naught square divided by 2R. Okay. There's another way of writing this. See, the current function was this I naught sine omega t. Quickly tell me, what is the RMS value of this function? I naught is a constant, put it aside. What is the RMS value of the sine function?
I naught by root.
1 by root 2. So this whole thing becomes I naught by root 2, correct? Okay. Similarly, EMF equation we had was E naught sine omega t. Its RMS value will be E naught by root 2. Okay. Now observe the power equation that we got, average power that we got. If you take it as like average power, if you take it as I naught square R divided by 2, 2 can be written as root 2 whole square. I naught by root 2 is the RMS current. So you can write the average power as I RMS squared into R. In terms of voltage, if you want, you got average power as E naught square by 2R. 2 I'll write as root 2 whole square into R. E naught by root 2 is the RMS value. So this becomes E RMS squared divided by R. Why we write it this way is just to make the formula simpler. Like in DC current, direct current, okay, when constant current flows through a resistor, we know power dissipated by the resistor is I square R. When variable current flows through a resistor, it changes to I RMS square into R. That's all. Just to draw a similarity between the formulas, we use this RMS value. And now you can understand the significance of RMS current. Root mean square value of a current. What is its significance? Root mean square value of current is that current, or see, when do you talk about root mean square? You talk about it in case of variable current, alternating current, right? But if this much direct current passes also, that same power will be dissipated. Do you all agree with this or not? If a direct current, let me just write DC. If a direct current of I RMS passes through the resistance R, then the power dissipated by it will be equal to the average power dissipated by the alternating current. Okay, so that is the significance of RMS current. RMS current of an alternating current, RMS value of an alternating current is like the DC current which would have given the same power output. Did you all understand this point? In an AC circuit, you will have alternating current. So it will produce variable power. It will dissipate variable amounts of power. Okay, but you can still find out on average power dissipated. The average power dissipated by an AC current will be equal to power dissipated by a DC current whose value is equal to IRMS. Okay, that is what is the significance of RMS current, and similarly RMS voltage. Fine, let's quickly solve one problem based on all this. Assume resistance is some 4 ohms and the EMF equation is given as 12 sine 100 pi t. Okay, I want you to do this quickly, write the current equation, then write the power equation, then calculate the average power dissipated by this resistor in one cycle. Solve this quickly. Okay. Isha, can you tell the current equation?
So formula or the equation?
Okay, tell the formula.
Formula E naught by R.
See, E naught by R is the peak current. But I just asked you
Okay.
current as a function of time. Okay, as the voltage keeps changing, the current keeps changing. How do you write current in a resistor? Or how do you calculate current in a resistor? Rishi, can you tell?
Sir, E naught by R and and sine omega t,
Okay.
and then
See,
from
you
there.
just have to divide the EMF with the resistance as it is. Okay. EMF is 12 sine 100 pi t, divide by resistance 4, 12 by 4 is 3. So it becomes 3 sine 100 pi t, that's all. That's the current as a function of time. Next, power as a function of time. You can use E square by R, you can use I square into R, it's your choice. I'll use I square into R. Square the current function, it becomes 9 sine square 100 pi t. That is I square. Multiply with resistance 4 ohms. So it becomes 36 sine square 100 pi t. That is power dissipated by the resistor as a function of time. Simple. Even if you do E square by R, you will get the same thing. 12 square is 144. 144 by 4 becomes 36 only. And the average power dissipated. Average of the sine square function is half. 36 by 2. 18 watts is the average power dissipated. Assuming everything is in SI units. Is this clear to all of you?
Sir, I have a doubt.
Yeah, tell me.
Sir, for the B1, I just got the number 33. What formula was I supposed to use?
How did you get only 36? What formula did you use?
Because one second, sir. So, uh, oh, my bad, sir. I didn't put the sign. Yeah, I
You
understood.
have to substitute the function as it is. Okay. Right. There's another way also to calculate average power by using the RMS values. You can write I RMS squared into R or E RMS squared divided by R. Now current function you got, this is the peak value of current, like 3 is I naught. Then I RMS will be peak value divided by root 2. So 3 by root 2. Substitute that here. 3 by root 2 whole square multiplied with the resistance of 4. 3 square is 9, 9 fours is 36 by 2 becomes 18 watts. So even if you do this way, you'll get the same answer. ERMS squared. Peak value of EMF is 12. That means the RMS value of the voltage will be 12 by root 2. Keep it as it is. Square it here. 12 square by root 2 square is 2 and resistance is 4. 12 square is 144 divided by 4 is 36 by 2 is 18. Whichever way you do, you will get the same answer. Okay, so let's quickly go through what we discussed today. Effectively, what we learned is what happens when an alternating EMF is applied across a resistor. Okay, we first discussed about RMS value of the sine function, 1 by root 2, then E naught by root 2. An alternating EMF applied to a resistor, you get alternating current. And a very important observation is that the current through the resistor and the EMF or the voltage across it, voltage across the resistor will always be in phase. If current is increasing or reverse, if voltage across the resistor is increasing, current will be increasing. If voltage is decreasing, current will be decreasing. They'll be in phase with each other. That's one observation. And based on EMF equation, we wrote the current equation today. I is equal to E by R. You can do the reverse also. If you know the current equation, you can write the voltage equation. V is equal to IR. Simple. And then you can find out peak values, RMS values, average in the positive half cycle, all those things. So any doubts in what we discussed today?
No, sir.
Fine. We'll stop it here for today. Tomorrow's class will discuss how to deal if an alternating voltage is applied to a capacitor. And if time permits, we'll also discuss inductor case. Okay. Directly applied to a capacitor, directly applied to an inductor. So needless to say, revise some capacitor formulas and come. Like how basic definition of capacitance, how charge and voltage are related, what is the formula for energy stored in capacitor, those things you revise. Tomorrow's class will be easy to understand. Okay, thank you all. We'll continue tomorrow.
Thank you, sir.